Hi everyone. Today we're going to be following on our topic of radioactivity, looking at the next part, which is a bit more in depth about beta decay, what is gamma decay, and also what is and what are the effects of ionising radiation. So there are quite a few of our SACE outcomes that we're going to be covering today. There's a few about what is beta decay and about how to balance equations for beta decay, and also similarly for gamma decay, so being able to explain which type of decay is going to happen, and also balance gamma decay equations, and also some of the properties of radioactive emissions. So comparing the different types of radiation and the strengths and the effects of their penetrating power, and what actually happens when this type of radiation interacts with humans and the effects on living matter. Right, so we've covered what alpha decay is, where a nucleus will emit an alpha particle, otherwise known as a helium nucleus. Today we're going to be having a look at beta minus and beta plus decay. So the first one is beta minus decay. So this happens when a nucleus has too many neutrons. So if it has too many neutrons and it's not stable, it wants to be in a nice stable state, one of those neutrons actually turns into a proton and an electron. So if it's got too many neutrons, it wants to have a proton, and that will actually increase the nuclear force within the nucleus and make it nice and stable. So for that to happen, a neutron has no charge, so to be able to keep a balance of charge, it has to turn into not only a proton, but also an electron. Now that electron doesn't belong in the nucleus, so that gets ejected or emitted from the nucleus. And because of the law of conservation of momentum, there's also another particle that has to be emitted, and that's called an anti-neutrino. And basically, we'll go through what that is in a second, but it gets ejected also from the nucleus. So the easy way to remember is beta minus is an electron because it's a negative charge, and also an anti-neutrino is given a little symbol of a V with a minus or a dash over the top. So it kind of looks like a minus as well. So those three go together: beta minus, an electron, and an anti-neutrino. Alright, so what's an antineutrino? So as I said, it's a little particle given the symbol with a V and a dash that kind of looks like just velocity. It's a particle, it doesn't have any mass, and it travels about the speed of light. So it only interacts matter with a very, very weak force, and it's particularly difficult to detect, but has been found experimentally, so that's how we know that it's there. Now, beta particles, unlike alpha particles, when they're ejected, they have a range of energies. So when the electron's emitted, it can have a range of different energy levels, and therefore a range of corresponding velocities that it might be ejected with. Okay, so the reason that it has a range is because beta emission is a three-body interaction, not a two-body interaction. So what happens is we have the nucleus, we have the beta minus particle, which is the electron that's being ejected, and also the antineutrino that gets flung out as well. So the way in which the energy is divided up between the beta particle, the antineutrino, and the nucleus depends on the angles, because we're talking about vector quantities. So that's going to mean that depending on the angles, that will depend how the energy is divided up. So therefore, there can be a range of energies that those particles actually have, as you can see by the little diagrams at the bottom there. Alright, so just to recap on neutrinos and antineutrinos, because these are really new subatomic particles for us. They travel at the speed of light, they have zero mass, so they're kind of like a photon. They have a really small mass because technically they don't exist when they're at rest, they only exist when they're moving, and they have no charge. They can only interact really, really weakly with other states, like other types of matter. Okay, so we have talked about beta minus decay, where an electron is emitted. Now we're going to talk about beta plus decay. So beta minus happened when a nucleus had too many neutrons and one turned into a proton. Beta plus decay is where it has too few neutrons and one of them is going to turn into a neutron. So a proton actually turns into a neutron and what's called a positron. Now, a positron is a positive electron, and it's basically the same as an electron but with a positive charge. And if a proton is turning into a neutron, it needs to get rid of its positive charge, so it throws out this electron that's positive, called the positron, and again, because a positron or an electron doesn't live in the nucleus, it's thrown out. And again, we get that little particle to make up the missing momentum. That is a neutrino. That's also emitted as well. So here we've got a proton that turns into a neutron, and its additional plus charge is emitted as a positron. That's why beta plus positron emitted. And you can see it's not an antineutrino this time, it's just a neutrino, and that's also emitted as well. So the easy way to remember this one, beta plus, positron, positive, and it's just a regular neutrino, not the anti or the negative version. So you can see here we've got carbon 11 turning into boron 11, and so we still have the same number of nucleons in the nucleus, but one of them, instead of turning, so the proton in the nucleus has turned into a neutron, so we've lost a proton, so that's why it's turned from carbon to boron, and then the positron, the little plus electron, has been emitted, and the extra energy for the neutrino has also been emitted. Alright, so we know how the universe likes to be balanced. So there's things like matter and antimatter. So for every particle there exists an antiparticle, which is identical in most ways, but opposite in charge. So it's like equal and opposite forces. So for electrons, we have positrons. For protons, we have something called an antiproton. For neutrons, we have antineutrons, neutrinos and antineutrinos. So when a particle and its antiparticle collide, they actually annihilate each other, and their mass is turned completely into energy. So in beta minus decay, we get the particle-antiparticle being produced. So the electron and the antineutrino, and we also have positrons with a neutrino. So electron and antineutrino, positron, neutrino. Okay, so the last type of decay that we have is called gamma decay, and this is slightly different. It's where the nucleus actually has too much energy. It's usually as a result of alpha or beta decay, and it's left still not quite as stable as it would like to be. And then the nucleus, like an electron would, if we have an excited electron, it goes to an excited state. The nucleus can be in an excited state too. And what happens is it falls back down to a lower energy state. And in this process, the additional energy is given off as a photon called a gamma particle. So you can see here we've got a helium-3 nucleus and another helium-3 nucleus. And instead of being a higher energy state, the nucleus falls back down to its regular or ground state. And that additional energy is lost as a gamma photon. So we all hear about radiation being bad. So what does that actually mean though? So these types of ionizing radiation that we've talked about today, there's alpha, there's beta, beta plus, beta minus, there's gamma, and there's also neutrons that can be emitted as well. So all of these things can be quite damaging especially to humans and to living tissue. But let's have a look at them in a bit more detail. So alpha particles, we know that their mass, they've got 4 nucleons, they've got a charge of 2 protons or plus 2. Now what a alpha particle can get through is paper, skin, clothes. So it can't go too far, but it can penetrate into human skin. Now beta particles, they can either be plus or minus. You can see here because they can be a positron or they can be an electron, and in which case either of those can be a bit more penetrating. They can get through plastic, through glass, or through light metals, and you can see in the diagram at the bottom there. Now, gamma rays they're electromagnetic waves rather than a particle, and basically they can get through dense metal, concrete, or even earth. So a little bit more dangerous, a bit more shielding required. And then neutrons, neutrons are actually the most penetrating out of all of the types of ionizing radiation. So neutrons are particularly dangerous, and they can get through water, through concrete, through polyethylene, through oil, and all the way through lead. So they need to be shielded really, really well. So I just used a term called ionizing radiation. What does that mean? So it's called ionising radiation because it can ionise atoms. And ionise atoms means that it can make an atom lose or gain electrons. So it can give them enough energy to lose or gain electrons. And that can be quite dangerous, especially in living tissue. So ionising radiation includes alpha particles, beta particles like beta plus or beta minus particles, gamma radiation, it can be protons, it can be neutrons, it can be X-rays, it can even be ultraviolet radiation like from the sun. So ionising radiation can damage human tissue, and basically it does this by causing chemical changes within our cells that actually produce toxins, and that comes as a result of having odd numbers of electrons which create different charges, which changes the normal chemical reactions that our cells undergo. It can actually kill cells. It can also cause damage to DNA, which can possibly go on to cause cancer. We know that all particles are moving in some way, and if we give them extra energy, they're going to be moving faster. And this happens in our DNA when there's like ultraviolet rays or different types of radiation hits our cells. And if it has enough energy, it can actually break off parts of the DNA, and then it can be copied and produce errors which go on to actually producing cancer cells. It can cause changes to DNA and in sex cells, so it can go on to produce mutations in further generations, which we have seen as a result of some radiation diseases. Okay, so the effects of radiation exposure on human health, it's not good. Although a dose of just 25 rems, which is what they use to measure radiation exposure, it can cause some detectable changes in blood. Up to 100 rems can have no immediate harmful effects. So that seems to be the limit. Doses above 100, we sort of start to get the first signs of radiation sickness, which can include nausea, vomiting, headaches, and some damage to our white blood cell counts. Above 300 rems, it starts to get really quite serious, and we can have things like hair loss, internal harm, damage to nerve cells and actual cells in the digestive tract. We lose much more of our white blood cells, which means that we're more prone to infection and makes you highly vulnerable to disease. And it also can reduce the production of platelets, so clotting agents in our blood, and you're also more vulnerable to hemorrhaging if you have undergone radiation sickness. So half of all people exposed anywhere above 450 rems, they die, and doses of 800 rems or more are always fatal because of all of the symptoms above. They might also suffer from fever or diarrhea, and as yet there's no effective treatment. So once someone has been exposed to really high levels of radiation, death generally occurs between 2 and 14 days. There's not much we can do to actually assist these people. So in time, if someone has been exposed to a lower dose of radiation and they have undergone some form of radiation sickness, survivors may be susceptible to diseases such as leukemia, lung cancer, thyroid cancer, breast cancer, and cancers of the other organs can appear just to the doses, because of the doses of radiation that's been received, and some damage has been done to their cells. So that all sounds really grisly, but there are things that we can do to try and minimise the effects of radiation on our bodies. The first one is to make sure that we increase the distance from the source of radiation. So to stay away from radiation, if there happens to be a radioactive power plant or a nuclear power plant nearby, to limit the distance it is towards built-up areas, that sort of thing. The other thing is to limit our exposure time. So if you do need to be exposed to a radioactive source in terms of medical imaging or something like that, we try to limit the time that that person is actually exposed to the source of radiation. And lastly is to use adequate shielding. So if you do go in for a medical imaging procedure, such as an X-ray, you'll notice that the technicians actually leave the room when they're doing the X-ray and leave you in there on your own. So that, because they're around X-rays all day, they're doing a few things there. They're trying to increase their distance from the source by leaving the room. They're limiting their exposure time to that X-ray source because they're around it all the time, and they're standing behind a shield. And you often find that you have to wear the lead apron as well to make sure that the only part that's getting irradiated is the part that needs to be imaged. So all of those things working together can help maintain your safety and limit your exposure to that radiation source.